forces is there's a lot of different forces. Okay? We have just basic net force, mass times acceleration. Okay? But net force is when you take away or subtract all the different forces acting against you. Okay? So that's where the challenge with forces will be. Does that make sense? We're recording. So the worksheet I plan to give will be honestly will be the tougher worksheet because the steps you do in question number 1 will be different than the steps you have to do for question number 2. Okay? With Madonna problems were basically always the same steps. For the most part, not always, but they were always at least very similar. With forces, question 1 will be a completely different type of forces question than question 2. It's more about just understanding where everything's going than it is about step 1, solve for time, step 2, do this. Okay? So there will be a challenge to it. But we'll be all right. Okay. So last time we talked about, let me go back to it for a second. Weight. We had weight and we had force applied. Remember weight? Weight is also called the force due to gravity. Good. Okay? Weight is the force due to gravity. F sub g is weight. We use the word weight. Okay? It's different than pounds. Weight is a force due to gravity, and we measure that in newtons. Okay? My weight, I weigh about 700. Because I'm talking about newtons, not pounds. Alright? Force applied was really, really basic. It was just whatever you push or pull with. There's no formula to it. It's just in a problem, what are you pushing or pulling with? I'm still here. Okay. Now we need to talk about this normal force. I want you to look at the picture because the picture's going away in a second. The normal force is going to be pointing, in this case it points straight up, but more so it's going to be perpendicular to the surface. I'll have a whole slide about that. And then we're going to talk about friction. Okay, so those are the things we want to talk about today and just get a better understanding of those type of problems. Alright, let me skip ahead again. There we go. So the normal force, remember we talked about Newton's third law, equal and opposite forces, right? I push down, the table is going to have to push back up. The surface has to push back up or I'd fall through it like a ghost table. Remember that? Okay, so the normal force is that equal and opposite reactive force. It's that it's a force back on the surface. So when you see normal force, it's whatever the surface has to push back up with so that you don't fall through it, or the object doesn't fall through it. Okay? Now, a lot of times, it will just be equal to whatever the weight is. Most of the types of problems we'll give, okay? I'm going to steal your book. Can I steal your book?
Sure.
All right. This book has, obviously, it has at least 2 forces pulling down on it right now. Okay? It has weight, the force due to gravity, pulling down on it. Okay? Which means it also has to have the force, the normal force, pushing back up. Equal and opposite forces. Alright? We'll move over there. So we have equal and opposite forces always. So most of the time, if you just have an object sitting here, and even if you're just pushing it one way or another, the normal force, which is the force that the surface has to push up with, is equal to the weight that is being pulled down with. So I would say probably 90% of the time that we have problems, and probably even more than that, the weight and the normal force will be equal and opposite. Or the normal force will just be equal to mass times gravity. Okay? There are instances where it's going to change. Because the normal force, if I push down harder on the book, well, that means the surface has to push back up. So now the normal force is going to be a little bit more. Because again, the surface still has to fight back against me. Alright? If I put it on an angle, weight pulls straight down. However, normal force is going to be perpendicular. I'm going to show you a picture later for that. Okay? In this case, also, the normal force is not equal to the weight. But 90, 95% of the time, you'll have something like this, even if I'm doing this, okay? So the normal force pushing back up is just equal to the weight pulling down. Okay? Okay. All right, now moving on. Still talking about normal force. Normal force is always, the word normal in math class, taking that from math class, means perpendicular. So anytime you see the word normal, it actually means perpendicular. Normal means perpendicular. Which again is why it's a lot, if the surface is flat, if you have a flat table, normal's pointing straight up, okay? However, if I go at an angle, normal is no longer pointing straight up. It's pointing still perpendicular to the surface, okay? So normal is always perpendicular. Weight is always down, but normal is always perpendicular, okay? And like I just said this before, okay, the normal force of an object will be equal to the force of gravity, or it will be equal to the weight only if it's laying flat. If it's at an angle, things change. Okay? Let me show you the picture. Oh, I'll wait, sorry. Let me pause. Here's an example where the weight is equal to the normal force. It's sitting flat, just like the book right there, okay? The normal force here is just equal to the weight. Which again, the normal force is just what the surface has to push back up with. The surface only has to push back up to fight against the weight, mass times gravity. So here, they're equal. I showed you if I push down, then it's not equal anymore. Also, if I go on an angle, because the normal force is always perpendicular. If something's flat, perpendicular means straight up. Okay? But now, if you have it on an angle, perpendicular doesn't mean straight up anymore. Okay? I want you to look at that area. So there's my normal force. That's what the surface has to push back up with, right? That much. That's only a little bit of this weight though. Okay? Only this much, when you have something on an angle, only this much of the surface, of the weight, is pushing perpendicular to the surface. Okay? Which means when you put something on an angle, okay, there's less of a normal force. There's less force that the surface, when I put this book up on an angle, the table doesn't have to push back up with as much force as before. Okay? Only a little bit now. Okay? So, that's an example. You don't need to copy down that picture right now. Down the road I'll show it again. Okay? But I just want you to understand that normal force, 90% of the time in this, 95% of the time, we're going to deal with flat surfaces doing this. Okay? If I do this, or if I do this, it changes a little bit. But we'll be able to handle that down the road. Okay? Alright. Now, next one is force of friction. The frictional force, the force of friction, there will always be a frictional force that will act in the opposite direction of the motion. Okay? If I push the stool in this direction, if I push the stool to the left, friction is going to push to the right. It's always going to be opposite the direction of the motion. Okay? It's also the opposite the direction of the intended motion. Meaning, if I don't get it going, even if I just kind of do this and I try to push, right now I'm giving it a force, but it's not going anywhere. Okay? So in this case, the frictional force is acting in the opposite direction of the intended motion. I want it to go that way. Frictional force is still going this way. It's still fighting against me. Okay? So I'm pushing this way. Friction has to fight against me. Okay? So frictional force is always opposite the direction of motion. Alright? And the formula is going to be this. Mu times the normal force. Okay? So it's going to be this new little letter, mu. Okay? See, is it on your cell phone already? Look on your cell phone there, Chelsea. Do we see mu there? No, we don't. Alright, this is how we do mu. You ready? U. U. me? Want me to do it again? I feel like I'm on Sesame Street when I do this. U, mu. One more time? Okay, one more time. U, mu. Mu is actually a lowercase Greek m. See how it's kind of an M? Okay? But I like my way better. So, mu is going to be this coefficient. I'm going to talk about it on the next slide. Okay? Mu is how much stickiness you have between two objects. Alright? But the formula is going to be force of friction is mu times the normal force. Okay? Whatever the surface has to push back up with, that times a certain amount of stickiness will tell you how much friction you'll have. Okay? Just remember that it's always in the opposite direction of motion. Can I move on with friction? There we go. Now, the coefficient of friction, again, it's a stickiness that two objects have between each other. So it's not the stickiness of one object, it's the stickiness of two objects in between each other. It's the interaction between two objects. Okay? So, there have been engineers for 100 years at least that have come up with different coefficients of friction, different mu's. You could go look in a book somewhere and it would have a list of coefficients of friction, a list of mu's, okay? So the coefficient of friction of wood on steel will be different than the coefficient of friction of wood on wood, okay? They have different coefficients because they interact differently, all right? The coefficient of frictions of basketball shoes on the basketball floor, on the court, will be different than the coefficient of friction of basketball shoes on ice. Okay? So it describes how two objects interact. Alright? Now, my best example of this is when I was a senior in high school, friends of mine, in our physics class, we had to do a physics of whatever we do, okay? And I had a friend that was a rock climber. So what he did was pretty cool. He did an experiment where he did a lot of application of physics, but one was he showed these really expensive rock climbing shoes. So he brought them out and he said, I spent $160 on these, okay? And these are very special rock climbing shoes. And the reason they're special is they have a very high coefficient of friction with rock. So he could step on at certain angles and still get a lot of friction when he was climbing a rock. So that was pretty cool, okay? And so what he did was, as part of the demonstration, he took a flat rock and had a car jack, okay? And so he had the flat rock and he stood on the rock and he had somebody start jacking up the rock to higher and higher angles, okay? And because there was a high coefficient of friction, we could go higher and higher and higher with that rock, and it wasn't until a very high angle that his shoes finally slid down the rock. Okay, does that make sense? So because he had a really high coefficient of friction, it meant he had a lot of stickiness, and he had a lot of stickiness at a lot of angles until a certain angle finally his shoes would slide down and didn't have any more stickiness to keep them up. Okay? Well, anyways, so then they did it, as a comparison, they had our teacher do the same thing, and he had these old Adidas Gazelles. Okay, I don't know if you've ever seen Adidas Gazelles, but they're like really old. They're really cheap suede shoes. They have white soles with the soles had a little bit of tread on them. Well, he had them for like, I don't know, 10 years or something. So the tread was all worn off. It was just a nice flat surface, anyways. So they had him stand on that same rock. So he stands on the rock, and they said, well, your shoes cost $40. My shoes cost $160. So you're going to have a lower coefficient of friction. So they stood on the rock, and the teacher stood on the rock, and they started jacking up the rock, and it went higher, and it went higher, and it went higher, and it went past the angle that the really expensive $160 rock climbing shoes could handle. And so he finally was at an angle better, okay? And it turned out that those cheap old Adidas Gazelles that are 10 years old, the white rubbery soles that he had on them were better for rock climbing than the really expensive ones. Okay? So there's my application of it. But again, coefficient of friction. The white rubber had a better coefficient of friction than the special rock climbing shoes. All right. So far, so good? Yeah. There will be no units for coefficient of friction. It's just going to be a number. Okay. Now, another thing about friction is this. You actually have two types of friction. You have static and kinetic. I want you to think about, has anyone had to move a really heavy piece of furniture or a big heavy box and you want to get it sliding along? There's two types of forces you'll have, okay? You'll have a force to get it going, okay? If I want to move this stool, let's see if I can do it here. If I move this stool, okay, there'll be one force to get it going, okay? Once it's moving, it's really easy to move around, okay? Let me do it over here. So here on the floor, I have one force to get the stool going. That's my static force of friction. I have to fight against the static friction. Okay? That's going to be a greater force. Once I get it going, it's really easy to move around. Okay? Once it's moving around, once the friction is going, once the chair is moving, the friction is less. So static friction is the force it takes to get something going, or the force you have to fight against to get something going. The kinetic force is the force you have to fight against once it's moving. So when something's sitting still, it will have more friction than once it's moving. This is actually something you need when you talk about cars. But let me wait a second here. Let's copy that. The static force will be always greater than the kinetic force of friction. The force it takes to get moving when you're driving along the road. Any idea?
What was the question?
What type of friction do you think your tires have when they're moving along the road? It was a trick question. The car is moving, but if you think about the tires, think about what a tire does. Okay, a tire goes down and up. Okay, here's my little tape. Okay, think about the tire. The tire just goes down and up. Okay, the tire doesn't move relative to the road. The tire is moving relative to the road. It's sliding. Sliding's bad, right? Okay, so when a tire is driving along, it's actually static friction. Now remember, static friction is better than kinetic. Okay, so what happens with your tires, if you're skidding, you're going to be sliding along much farther distance. It's going to be a lot harder for you to stop, and it's going to take a much longer distance for you to stop if you're in a skid. Okay, that's why they have anti-lock brakes. If you think about anti-lock brakes, now pretty much every car has anti-lock brakes. Okay, when I was in high school, they just started coming out. All right, and the idea with anti-lock brakes is this: before anti-lock brakes, you're driving along, you slam on the brakes, and the locks just seize. Right? They latch on and they stop that tire from spinning. Well, the problem is if your car's still moving, now you're just in a skid. Okay? Even if it's dry on a dry surface, on dry pavement, it's going to take a longer distance for you to stop. But especially in snow or water, but especially in snow, if you're in snow, you lock up your brakes and you're going to be skidding for a long time. It's going to take a much longer distance for you to stop. Okay? When you drive in snow, that's why you never ever want to pull on your emergency brake to stop when you're in snow, or just pull on your emergency brake at all, okay, to stop. All right, that's why I think they started calling them more parking brakes, so people don't think in an emergency, pull the emergency brake. Okay, because if you pull the emergency brake again, the brakes lock up, and there's no way for that tire to go back into this motion. Okay, so you'll have those big long skid marks along the road because the brakes locked up. Okay, so what anti-lock brakes do is when you slam on the brakes, it'll spin and it'll apply the brakes, but all of a sudden if the wheel stops and the car's still moving, it lets go of the brakes and lets it roll a little bit more and then slams on it again. Okay? So anti-lock brakes will squeeze and let go, squeeze and let go, squeeze and let go to keep this motion on your wheel and not have that motion on your wheel. Does that make sense? Thank you, sir. So there you go. There's another application. Now, what about when you're, if you're doing the burnouts or whatever? Okay, this might be too soon, but if you're in a, what do they call it in the movie? In the Too Fast, Too Furious, Tokyo Drift, right? Okay, R.I.P. Okay, sorry. But with the Tokyo Drift or with any kind of drifting, the idea is the opposite. They want to get kinetic friction. They want to be able to get that skid. Okay? They want to have a lower coefficient of friction on those tires so that they can skid along and do the turns or whatever they need to do. Okay? But again, if you're spinning out, if you're burning out, there's a much lower amount of friction now than when it's just going up and down compared to the road. Okay? So that's static versus kinetic on your tires. Alrighty, almost done. I love it. I think everything's freezing. Got the Intel computer. Alright, you don't need to copy this down. Let me go back a second and see what I missed. Nope. Aye. I'm going to have a bunch of examples coming down the road. I'm going to do, like I said, with forces, there's a bunch of different ways to, we just have to keep track of forces. There's no step one, step two that always are the same, okay? Forces are a little bit different. We have to say, all right, well, what's going this way, what's going that way? Okay, the way I'm going to assess you, you had a worksheet last class. I assessed you on F equals MA and weight equals mg, okay? And being able to tell the difference between weight and force, or weight and mass. I'll say that better. Weight and mass, okay? I'm also going to assess you on understanding which direction net force would be and understanding where all the other forces will point. Okay, we will have problems where you have to calculate friction or calculate something else from it, where you have one force going this way, one force going that way, what's the net force? I will have problems like that. Those would be the tougher problems, okay? This would be a general problem you have to do. I'm going to talk about this later, all right? Then it would get a little complicated. This would be the push the envelope problem, the one extra little problem you have near the end. This is a little trickier when you go on a ramp, okay? I'll give that later. All I want you to do right now is copy down these formulas here, and this is it for today. All right? Here are all the different forces. Now you'll see we talked about normal force usually being mg. You'll put the cosine theta in. You want to keep it as cosine theta. If something is flat, what's the angle? If something's sitting flat, what would the angle be? 0. So if anything sits flat, the angle is 0. Okay? What's cosine of 0? Any of my math people know? Cosine of 0 is 1. Okay, so really, a lot of times, I'm going to give you this formula, but 90% of the times, things are going to be sitting flat anyways, and this is just 1, or hidden. We don't even need to write it down if it's a flat surface, because it'll just be 1. Okay? All right, we'll copy that, and we'll move on from there.